In this talk I'll discuss the use of the lightweight software language processing approach which we developed using the ANTLER parser tools and the code generation transformation language. So this is meant to be an approach for software language processing, which would include language translation and tools for domain-specific languages. And it's a grammar-based approach, so it uses the ANTLER parsing tools and a specialized transformation language that works on parse trees. And this can be applied to a wide range of tasks, provided those tasks are based on grammars and on parse trees. So it's very much a textual language processing approach. Now, the reason for doing this was because of my experience as a consultant for industry, and I was a consultant for a major finance company who wanted to introduce MDE. And one of their problems and challenges of introducing MDE was the lack of MDE skills in the domain and the need for the tools and languages used to be usable by general software practitioners who wouldn't have the specialized MDE skills. And in general, MDE needs to be sustainable in industry in the sense that it should be usable by general software practitioners, people who graduate from a computer science degree, maybe with a little bit of extra training, but they shouldn't have to have a deep knowledge of model-driven engineering in order to use the tools. And therefore, we looked at pragmatic approaches which could be used more generally, and that's how we came up with this ANTLER plus CGTL approach, where the focus is more on grammar and there's no need to involve the use of metamodels and models of metamodels. Now, ANTLER is a well-known technology for writing grammars, for programming languages, but also for other languages. There are grammars for Z, for example, and for other domain-specific languages. ANTLER will take your source text and turn it into an abstract syntax tree. To process those abstract syntax trees, we use the CGTL, and the CGTL is essentially a text-to-text transformation language which can produce target text in any language from source text that satisfies a grammar. And that can be used to define this chain of processing whereby the parser produced by ANTLER takes the source language code and text and turns that into parse trees, and the CGTL scripts then can produce text in any target language. So we effectively have a language 1 to language 2 transformation based on grammar. So the question is, could that actually be used for a range of tasks, a range of practical tasks? Is it actually a practical approach? We can be fairly confident that it's usable, but the question is, can it actually do useful things? And we're going to look at the DSL tooling and also language translation, program language translation. So what is CGTL? CGTL defines functions on abstract syntax trees. Essentially, it is a function from abstract syntax trees to text. And it's organized, a script is organized as a set of rule sets named by a name and a sequence of rules, an ordered sequence of rules, and each rule has a left-hand side pattern which matches against certain kind of parse trees, satisfying that pattern, and it produces target text based on that source. Generally, the structure of the scripts follow the grammar for the language, the source language. Usually each grammar category will have a corresponding rule set, and each grammar production will have a corresponding rule. Now, they may have extra rule sets for internal processing and the grammar productions might be broken down into specialized cases to deal with distinctions that are not necessarily represented explicitly in the grammar. The semantics of this language is that each script is a function from terms, abstract syntax tree terms, to strings, and an abstract syntax tree term is essentially a tree where we have a label which is the tag, the non-terminal of the grammar, the non-terminal name of the grammar, followed by the sequence of terms, the subterms of that term. And the rule set will have this label, the tag label, and individual rules then will match against these terms, the sequence of terms. We use variables _I in the left-hand side of a rule to match the individual subterms, and the target right-hand side is constructed based on the translations of those subterms. So on the right-hand side, when we write _I, what it means is the translation recursively of the subterm. So essentially this function here is defined recursively by the structure of the source terms, and the termination of that recursion is when we meet symbols or lexical tokens which don't have any decomposition. Here are some actual examples. Let's say we're processing a language which has basic expressions and binary expressions. Basic expressions are essentially identifiers, and binary expressions could be sums, let's say. So we could have an input term which is an OCL binary expression, each of its subterms is a basic expression, or it's a token symbol plus. So that's basically the term A plus A. Now the rules here say that 0 plus anything is that thing, and so on. If we have two items being summed, then the result is the item times 2. And these rules are applied in order, so that if we match this situation, then this rule is applied, otherwise the general case is applied. So if we have this input A plus A, we're going to get an output A times 2 from this rule, third rule. Now DSLs are widely used to specify particular software functionalities, particular kinds of software systems, for example machine learning systems. The DSL will normally have a grammar, so we can therefore process a DSL model, a DSL specification using the same approach that we propose, and the approach was applied to a DSL for natural language processing and a DSL for mobile application specification. And then language translation from program translation is a very common and very widely used technique for legacy code recovery, renewal, translating from one language to another, for example Python 2 to Python 3, or more generally from a legacy language like COBOL to a modern language like Java. And we used the CGTL approach to implement abstraction transformations from various source languages to UML OCL, and that is essentially design recovery, abstraction of the source. It can then be used for forward engineering to any target language. So natural language processing tools. The NLP DSL represents pipelines and processing steps that you would undertake in a natural language processing task. For example, a natural language processing task might include putting part of speech tags on items in a sequence of words, and selecting those words, selecting sentences which have a verb. So these are typical kind of NLP tasks, and the DSL represents them in a kind of SQL syntax. So we can say create temporary table WD set as the selection of the X and pos tagged X from the data set, meaning that we create the word set as the part of speech tagged version of words from the data set. And likewise, the verb set is those words or word sequences which have a verb. We define NLP CSTL to define the translation from that DSL to Python. Python being used because it has the natural language toolkit, NLTK, for doing NLP tasks. Some of the rules in that translation are like this. We have variations on select, and in general we could have a select which collects together result values, and that can be expressed like this in Python, or we can have a select which filters, and that could either be a select distinct producing a set or a general select producing a sequence. And that produces the following in Python from that example's DSL script, DSL specification. So we construct the part of speech tagged for the data set elements, and we create the filtered sequences in the second case. And we ended up with quite good results, and that it was shown to be a quite efficient approach, and on realistic NLP tasks. The second DSL was for mobile app specification, a much larger problem, and the source in this case, the DSL specified classes with data, and it specified what kind of data that was, if it was persistent or non-persistent, and if it was remote or local data. And we want to generate Swift UI and Swift code which handles that remote or local data, either as local databases or as Firebase cloud data stores. And we also want to produce a UI. So there's quite a lot of code being produced from what might be a very small specification. Now that's a much larger task, and it needed the construction of 15 separate CGTL scripts. Generally each script produces one kind of output. These scripts might take the same input, but they'll generate different outputs, because in this situation we're generating different parts of a mobile application from the same source information. Nonetheless, it was a practical process, and we applied this to a wide range of different apps, and again the time was found to be the time for processing was found to be a reasonable time, 6 seconds on average. Now, program translation is again a different kind of language processing task, and we want to do abstraction of various source languages to an intermediate form which is represented in UML OCL, and then do forward engineering to various target languages. And we want to compare the translation accuracy of that translation from source to eventual target by comparing the percentage of tests which give the same result in the source and target. And those are the results. So translating from Java to Python, for example, we get a 93% accuracy. This goes down for more unusual languages, or languages where the semantic difference between the source and target is larger, like VB6 to Python is a bigger gap, and therefore lower percentage of accuracy, but it's still a reasonable percentage. And these are also fairly efficient. We look at this column is about 4 seconds for the largest of these applications as an abstraction time. That compares reasonably with the actual code generation from UML OCL to the target language. This forward translation is also written in CGTL. Both of these are written in CGTL. The Swift and Java 8 forward translations are written in CGTL. Now, of course, the CGTL is a limited language. It's not a general purpose transformation language. It can do some transformation tasks based on pattern matching, but that pattern matching only extends to the immediate subterms. So if we look at this example of the expression simplification, it's matching on the immediate subterms of a term. It won't go deeper into, for example, the elements of the _1 here. It only looks at the top level of that term, the only OCL binary expression term. So there's limits on what can be done. In some cases, you can do more detailed analysis of the data by recursive application of functions, but it's a rather complicated thing. It also depends on the fact that we have grammars for the languages to be processed. That's an essential. Now, in terms of program abstraction, we have limits due to the size of the 3GLs, so we can't deal with all of Java's libraries, for example, because that's an enormous collection of code. We can only look at the core language and the main libraries as a source of translation. Nonetheless, if someone wants to extend what we've done, then that can be readily done by extending the CGTL abstraction scripts. That's the advantage, that somebody can change those scripts without needing advanced knowledge, and they simply need an understanding of the source language and the target language in order to write those scripts. So in conclusion, we've defined a practical approach which enables a lightweight use of MDE for the language processing tasks, especially for supporting DSLs and for program translation. And this has been shown to be usable by general software practitioners. There's no use of metamodels and model transformation languages. Instead, it's based on grammar. And this is applicable to a wide range of language transformation tasks. The other thing also is it's relatively low resource utilization compared to more heavyweight tool support.